Hi, Professor. My name is Ziyang. Today I'm going to have a presentation about topological sort, which is about our final project presentation.
And I'm Siu Xiao.
I'm Hui Jun.
卓然.
One of the most important application of the topological sort is using it to solve the circular import problem. There are two cases of the circular import problem. The first, in most scenarios, the circular import problem occurs when the programmer tries to accidentally name their working file the same as the module name, and those modules depend on each other. In this way, the Python opens the same file, which causes a circular loop, and eventually it will throw an error. For example, if you name your file as random.python and try to import from random, import radiant, it will throw a circular import error. The second case is when you have two files or packages, which will include the code for importing another package, but these two packages or files will try to import each other. So this way, it will also throw a circular import error because it will cause an infinite loop of trying to import two Python files or packages. Next, please. So our project will focus mainly on the course schedule problem. It will try to solve a task of scheduling a set of courses with different prerequisites. In a way, it will avoid cyclic dependencies. For example, if a course A requires course B as a prerequisite, and the course B requires course A as a prerequisite, it will be impossible for us to determine a valid course schedule because it will cause a circular dependency problem. Next, please.
What's a problem we try to solve? Our task is to design an algorithm that ultimately solves the dependency problem or detect if there are cycles in the graph. How to illustrate? We consider the course selection problem where we take a list of courses and its prerequisites to calculate a sorted list of the courses, which represents a feasible order to complete all the courses. Lastly, the main takeaway is if you ever encounter a problem where dependencies are an issue and you wish to find a way to solve that problem, you can model it as a graph problem and apply the algorithm we used. Next, please.
This part, we're going to show you the solution for the problem. First, we organized and recorded the course of computer science from the official website of NEU in Excel. As you can see, each course has its own code. For example, the code of the course Mixed Reality is CS4097, and the code of the prerequisite of the course is Cs3540. We gathered the data into Excel and assigned unique ID for each course and its prerequisite. Next, please. We sorted out 81 courses and added the ID into the nested list so that our application can access the data easily. Each list in the nested list has two elements. The second element is the prerequisite of the first element. Each course is allowed to have more than one prerequisite. Next, please.
Okay, let's start with a small sample of the course selection problem and work out through it and show you how our algorithm seeks to provide a feasible plan to complete all of the courses. Given that there are 5 courses that we wish to take and the prerequisites for the course are represented as a list of lists, the first pair of elements, 1, 2, means in order to take class 1, class 2 needs to be taken first. And in our algorithm, we will store this prerequisite relationship in an adjacency list, as you can see on the right here. Due to the fact that the problem involves a graph, we will need a way to traverse through it. In this semester of CS5800 algorithm, we learn about depth search and also breadth search. For this project, we decided to go with depth search. So to keep track of if there are any cycles, we utilize a set data structure where we would add courses onto the set if the course is being visited. Also, to track whether the course is already visited, we use another set to track that information as well, to avoid visiting the same course twice or more. And during the depth search, we will have two different base cases. Case one, if the course being visited right now already exists in the cycle set, this means that there exists a cycle. We will return false in this case, indicating that the course schedule has conflicts. And case number two, if the course being visited right now already exists in the visit set, this means that during previous depth search, we have already visited this course. We should return true to show that since this course is visited, we do not need to check whether its prerequisite has been satisfied, because it would have been checked during previous depth search iterations. And the main idea for this depth search is to check whether the course being visited has a cycle or it already exists in the visit set. If not, we would continue to visit the prerequisites of the course that is currently being visited. This means that we need to call depth search on the prerequisite as well to check whether its prerequisites has other prerequisites. During the depth search, to check whether a prerequisite can be completed without encountering any cycles, if during any iterations it returns false, it means that there's a cycle. Then the course schedule has conflicts. Otherwise, during depth search, if nothing has returned false, it means that the course schedule can be completed. And to get the order in which students should take the course, we are maintaining an output array to append courses to it if there are no cycles and its prerequisite can be satisfied without encountering any conflicts. And let me give you a visual walkthrough of how this algorithm works. Let's start with the first node. We are calling depth search on the first node. As you can see that it has two neighboring nodes, node 2 and node 3. When we are visiting the node, we are adding it to the cycle set every time. And we are also calling depth search on the neighboring nodes. So we will continue with node 2. Node 2 will call depth search on its neighbor. This will keep on going until we hit node 5 over here on this here. And when we hit node 5, there are no more nodes to visit. Then it starts to pop back on the call stack and continues to append to visit set and upper array. Until we reach node 1, you will try to visit node 3 again, but it will hit base case 2, where node 3 exists in the visit set already. It will just return true. Now, lastly, you can see the course plan is stored in the output array. And this is the order in which the student should take the courses without any conflicts. And to give you some limitations and weakness for our project is that we did not consider other factors like the course availability, student preference of the course, and professors' teaching style. To enhance our algorithm in the future, we would like to consider these and modify our algorithm to make it more interesting and usable.
We all learned a lot from the project. We always think that algorithm, including topological sort, is a difficult course since it's too abstract. There are lots of numbers, graphs, and mathematical formulas. Through doing this project, we combine topological sort with course schedule problem in our real life, which gives us deeper understanding of topological sort and helps us to go further on the road of algorithm. Next, please. We truly feel the greatness of the algorithm inventors. Topological sort is really powerful since which solves the problem that has troubled us for a long time. We all admire the intellectual brilliance of these algorithm inventors. This is the end of our presentation. Thank you.
Thank you.
Thank you.
Thank you.